Alright gang, here we go. This is for Chem 1, Unit 14, Part 3. We're going to talk about weak acids. Alright, now this is one you need to pay attention to. This is where the rubber meets the road. This is the hardest thing we've done all year. It takes into account a ton of different things. You have to pay attention. You have to do your practice problems. You have to try, or you're just not going to get it. Unless you're just one of those students that are naturally gifted at chemistry and just can understand things just without trying hard. All right. Props to you. You lucky few, but for the most of us normal people, we actually have to try to understand things like this. So this stuff here, vitally important. You need to try. All right, you need to pay attention, do the notes, do your practice problems, or you're just going to miss these questions. All right, now first we need to review just very briefly what we talked about, strong acids versus weak acids from back in Unit 12, I think. So anyway, remember a strong acid separates completely, okay, into ions when it's placed in solution, but a weak acid only does partially, okay, and we talked about this, how we have the 7 strong acids, and we had that saying to remember when we had like the high bromine and chlorine and all that stuff, right? And so we had those 7 strong acids, they dissociate completely, so this symbolism here, remember our acids are proton donors, so a lot of times when we're talking about these things, we'll put an H in front of whatever it is, saying that that is the proton that can leave. Okay, so we have an HA that's going to A minus and H plus. Okay, and so this is like the generic way to write out acid equations. Now, weak acids, all right, they do not completely ionize; they only do so partially, and so we use an equilibrium arrow. So this HA is in equilibrium with A minus and H plus. All right, notice that it's the same general reactants and products, but the big difference is strong acids completely dissociates, but weak acids can go either way. So that means essentially that you've got a weak acid right here. Right, this guy is a weak acid, but that also means that this guy here would be classified as a weak base because he can absorb a hydrogen to turn partially into the HA over there. All right. So ionization of a weak acid. So remember we talked about equilibrium. We talked about the idea of KEQ. Remember KEQ was equal to the concentration of the products over the reactants. If you don't quite remember how this works, go back to the part 1 video. All right, concentration of the products over the concentration of the reactants. And so this term, the Ka, is an equilibrium constant, but specifically it's for our generic reaction that we just looked at, where HA is in equilibrium with H plus and A minus, right? And so this Ka can give us the equilibrium constant of this, and specifically because it's for the action of a dissociation or an ionization of an acid, we call it the acid ionization constant, okay, Ka. All right, and we use it the same way, we determine it the same way we determined KEQ. Remember, it's a capital K, not a lowercase k. I don't know how that snuck its way into my presentation. But anyway, capital K. So for a generic weak acid equilibrium, how would our Ka be equal to? Well, remember, Ka is found the same as our KEQ, so it's the concentration of the products over the concentration of the reactants. Products are H plus and A minus. Right, so it'd be concentration of H plus times the concentration of A minus, all over the concentration of our HA. All right. So essentially, what this tells you is, well, what is the relationship? Remember, the bigger our K value is, the more products we have. So a strong acid, something that makes a lot of H plus, will have a very large Ka value. Something that does not make a lot of H plus will have a very small Ka value. So this Ka value essentially tells you how strong or weak your acid is. The stronger the acid, the higher the Ka. Okay, remember, because the strong acids completely dissociate, and things that completely dissociate or go towards more dissociation are things that are going to make more products, and that means your Ka is going to be bigger because your products are on the numerator side, so the bigger your numerator is, the bigger your value is. Okay, so here's just some example of some acids here. Hydrochloric acid, we know that's one of our strong acids. Its Ka value is 2 times 10 to the 5th. All right, that's pretty big. That's a pretty big number. That's like, 200,000, something like that. A nitric acid, also a strong acid, okay, but its Ka value is only 25. Still a strong acid, though it completely dissociates. Makes lots of products. No HNO3 is left over. All right. However, hydrofluoric acid, well, this is a weak acid. This was not one of our 7, and its Ka is only 3.5 times 10 to the minus 4th. All right, notice that it's much, much smaller. We have a big jump between our strong acids and then our first weak acid on this list. Acetic acid's Ka, that's a weak acid. Vinegar, right, is 1.8 times 10 to the minus fifth, and then we have ammonium and water. Okay, and water has a very small Ka value. All right. Notice also, so this is for specifically for acetic acid, and they've listed out the molarities, different molarities, 0.1, 0.05, 0.01, 0.005, and 0.001, and they tell you the percent ionization. So essentially, how much of our acetic acid ionized, and and they show you these concentrations. All right. And so what we can do here is, for any given row, we know now that the Ka value, well, the K for the Ka for acetic acid when it breaks down is going to give us H3O plus times the concentration of the acetate, right, CH3O minus, over the concentration of that acetic acid, CH3COOH. Right, and so we can use these values here to figure out what our Ka value is. And it's pretty interesting that if you do all this and you calculate your Ka values, look at all these values right here. Notice how it doesn't really matter what our initial concentration was. Our Ka value is still essentially the exact same. Oh my goodness, I just did something really funky with my... I'm sorry. So notice that our Ka values are essentially the same all the way across. We have 1.79, 1.82, 1.81, 1.82, 1.82. This is really different. Again, remember our K value, we talked about this when we talked about the equilibrium constant, but our equilibrium constant can only be changed by changing the temperature. And that's true for our Ka values. It doesn't matter what our initial concentrations were. Our Ka values can only change based on temperature. So as long as we're on the same temperature, we can use the... All right, let's try a couple practice problems here. All right, so it says write the equilibrium expression or equation and associated Ka expression for this weak acid, meaning acetic acid. So acetic acid is CH3COOH. All right, and it's going to be reacting with water, and we know it's a weak acid, so it's going to be forming an equilibrium. All right, and so this is an acid-base reaction. All right, acids donate a proton, so we get CH3COO minus because it got rid of that last proton. All right, and then this water is going to accept that proton, so it becomes H3O plus. All right, so you get acetate and water. Now, if we think about the states of matter of these guys, the acetic acid is aqueous because it's an acid. The water is liquid because it's pure water, and then this guy is going to be aqueous, and so is the hydronium. All right, now if we find the Ka expression, well, we know Ka is equal to products over the reactants. So we're going to look at the products. All right, they're all aqueous, no solids or liquids, so they all count. So it would be CH3COO minus times the concentration of H3O plus. All right, and then on the bottom we'll have acetic acid. All right, no water because water is pure liquid, and liquids and solids don't belong in our equilibrium expression. All right, so that's that. Now this next one is where the rubber meets the road. This is the fun stuff. Okay. Now it says calculate the concentration of acetic acid and acetate at equilibrium if the pH was found to be 4.50. All right, and it says the Ka is 1.8 times 10 to the minus fifth. All right, so we're going to use a new tool, okay, called an ICE table. All right, and this ICE table stands for initial, okay, change, and then equilibrium. All right, initial, change, equilibrium. So we've got, all right, so the way this works is it helps us keep track of what's going on when we form equilibrium. All right, so what goes on here is we're going to write out our whole chemical equation up here. So we've got acetic acid, CH3COOH, all right, is reacting with water, okay, and is in equilibrium to form acetate, CH3COO minus, and our hydronium. All right, and so what it says is we're trying to find, and you can imagine that this is really just a table, right, like this, initial row, change row, and then each of these guys gets their own little column, okay? All right, and so we got to think about what's going on at each of these different stages, okay? And it says what we're after is we're trying to find the concentration of acetic acid and acetate at equilibrium. So that means what we're really trying to find is what are the values that are going to go in here in our table and here, the acetic acid and the acetate. Now we know whenever we started, our equation here, we're going to start with some amount of acetic acid. We're not quite sure what that is right now. They didn't tell us, so we're going to put an X in. Now the water part, that doesn't matter because it's a liquid. It doesn't affect our equilibrium. It doesn't go in our expression. So we're going to just draw lines through that because it doesn't matter. Now when we first started, we're going to have 0 acetate and 0 hydronium. Okay, so we'll put zeros in for those guys. So we've got our acetic acid, we've got 0 acetate and 0 hydronium. All right, now we know for sure, okay, that our acetic acid is going to start dissociating into acetate and hydronium, right? That's what's going to happen in this reaction. We don't know how much, so we're going to say this is going to go down by some amount. We don't know how much it is, but it's going to go down by some amount, so we're going to call that Y. And whatever this goes down by, this is going to go up by that much. Okay, and the hydronium is going to go up by that same amount. All right, so we know at equilibrium our acetic acid is going to be X minus Y, and our acetate is going to be equal to Y, and our hydronium is equal to Y. All right, so that's kind of where we're at. So we got two variables, not a lot to go on, right? So we got to kind of come up with another way. So is there a way we could figure out what one of those variables are? Well, the X variable, we don't really have anything to go on the X variable because they didn't give us any initial concentration of acetic acid. But the Y variable, we know that the Y is going to be equal to the concentration of hydronium. And we also know what the pH is. Remember, pH, okay, is the same, is found by taking the negative log of the concentration of hydronium. All right, so we can take this guy, all right, and remember we can do our log backwards here. So that means the concentration of hydronium is equal to 10 to the negative pH. All right, so we can plug in 10 to the negative pH, and 10 to the negative 4.5 is equal to 3.16 times 10 to the minus 5th. Times 10 to the minus 5th. So that means our concentration of hydronium is equal to 3.16 times 10 to the minus 5th. So what that really means is that our Y value, okay, our Y is equal to 3.16 times 10 to the minus 5th. All right. So that means at this is equal to the concentration of acetate. All right. Well, that's pretty easy. Okay. So that's the concentration of acetate. Now we can start plugging things in here. So now we know at equilibrium our acetic acid is X minus 3.16 times 10 to the minus 5th. All right. Our acetate is equal to 3.16 times 10 to the minus 5th. And our hydronium is equal to 3.16 times 10 to the minus 5th. Okay, all right, we're starting to make headway here. So we also know we still have to figure out what X is so we can subtract and then we'll be done. Because now we have half the answer. We have the concentration of acetate. So now we got to find the concentration of acetic acid. Now, we know that the Ka is equal to the concentration of acetate, CH3COO minus, times the concentration of hydronium, divided by the concentration of acetic acid. Okay, all right, so we got that on the previous slide. Now all we have to do, if we look at this, we've got three things that we can plug in. We have a Ka value, that's this right here. We have our acetate and our hydronium, that's this value here, and now we have this. So now we can start plugging things in. So if we rearrange this to solve for acetic acid, then that means the concentration of acetic acid, CH3COOH, is equal to CH3COO minus, all right, yep, concentration of CH3COO minus times the concentration of hydronium divided by the concentration, or divided by the Ka. We can just start plugging things in. Since acetate and hydronium equal the same thing, this just becomes 3.16 times 10 to the minus 5th squared divided by the Ka value, which is 1.8 times 10 to the minus 5th. All right, so we'll take that and dodge around my face here. So that means our acetic acid concentration, so we'll take our value, square it, divided by 1.8 e to the minus 5th, and we get 5.5, or 5.6 times 10 to the minus 6th. 5.5 times 10 to the minus 5th. And so that is equal to the constant. That's equal to our X value, which is not our X value, that's equal to X minus Y. And since we don't need to solve X, then we're good. So this is equal to the concentration of acetic acid. All right, so that's pretty toughy. That's a tough problem for you guys, yeah? We had to do lots of stuff. Let's just recap real quick what we had to go through. We wanted to find the equilibrium concentration of acetic acid and acetate. We set up our ice table, right? We didn't know, and we just started plugging in things that we knew. We knew we started with some amount of acetic acid, but 0 acetate and 0 hydronium. And we knew this had to go to the right. So we're going to lose some acetic acid, we're going to gain some acetate, we're going to gain some hydronium, and then these would be our equilibrium values. All right, and it was important we did this because now we've established that the acetate and hydronium are going to be equal to one another. Then we worked backwards from our pH in order to find the concentration of hydronium. All right, and then we were able to take that value, plug those two values into our Ka, and solve for the concentration of acetic acid. All right, let's try another one. It says calculate the pH of a 0.25 molar solution of acetic acid. All right, so we're doing acetic acid again because evidently I'm not very creative. All right, so set up our ice table. First thing, all right, and we know it's an ice table because number one, I told you up here. Number two, it's an equilibrium because this is a weak acid. All right, so we got CH3COOH plus H2O. All right, whenever you do an ice table problem, always just write out the chemical equation. All right, CH3COO minus plus H3O plus. All right, so we go ice, ICE. Now initially our concentration was 0.25. It's kind of nice that they gave us that to start with. Water doesn't mean anything, so we're just going to ignore water. And we're going to have 0 acetate and 0 hydronium to start. Now our change, we're going to lose some amount of acetic acid because we got to go to the right because it's an acid. So we're going to form hydronium. All right, so we're going to gain some amount of this and we're going to gain some amount of this. So at equilibrium we'll be at 0.25 minus X, X, and X. All right, so now all it is a matter of we want to solve for what X is. All right, so that's pretty easy. We know the Ka value is equal to the concentration of CH3COO minus times the concentration of H3O plus over the concentration of CH3COOH. Okay, now we can start plugging things in. We know that the Ka is 1.8 times 10 to the minus 5th is equal to, this guy is x, this guy is x, so it's equal to x squared over 0.25 minus x. Okay, now we're going to just now we're going to solve for x, but there's a trick we can do here. You have to look at these two values. This 0.25 and this 1.8 times 10 to the minus 5th are if you were going to write this in scientific notation, this 0.25 would become 2.5 times 10 to the minus 1st. All right, so we'll just write this off to the side real quick so you can visualize it. That 0.25 would be 2.5 times 10 to the minus 1st, right? It would just be that. And you look at this 5 and this 4, or this 5 and this 1, and they are 4 apart from one another. So that means that we can neglect this x. If they're more than 3 apart from one another, 3 or more, we can neglect this x. So that x is going to go away. We just don't care about it. So we're just going to knock it out of the park. All right. So essentially, what we come down to is 1.8 times 10 to the minus 5th is equal to x squared over 0.25. So we can solve for x. X would be equal to 0.25 times 1.8 e to the minus 5th, and then take the square root of that. All right. And so this becomes 2.1 times 10 to the minus 3rd. All right, so that's our x value. All right, and then it asked us, well, what's the pH of this guy? Well, the pH, remember, our pH is equal to the negative log of the concentration of hydronium. All right, and our concentration of hydronium is that x value, so we'll just take the negative log of 2.1 times 10 to the minus 3rd. All right, so we take the negative log of our answer, and we get an answer of 2.67. Remember, pHs, the sig figs start after the decimal point. Okay, so there's a lot of stuff here. Ice tables were just barely, but ice tables are really, really, really important chemical concept that you used all the time. If you plan on taking college chemistry at all, you will do ice tables a lot. Okay, so make sure, now is just your briefest toe in the water experience with ice tables. They are confusing, they are hard. All right, but you just need, the only way I know how to do them and learn how to do them is to do practice problems. Ask questions while you're doing them. Take them one step at a time. Write things out I cannot do these problems in my head. I have to write them out. If I try to do them in my head, I always make mistakes, or there's a chance that I get the wrong answer. So even I've been doing these ice tables since, been doing these ice tables as of this recording for 13 years. All right, and I still have to write the suckers out. All right, so don't be embarrassed that you have to write these out to think through them, and so on and so forth. All right, so do your practice problems. Let me know if you have any questions. Let me know when you have questions, and I'll see you on the flip side.